This video is for topic 37A, inverse functions graphically, finding and verifying. Included functions in this particular section include linear, quadratic, square root, cubic, and cube root functions. In Unit 2, Topic 1, we discussed the idea of functions and of inverse functions, and we found that inverse functions have the following properties. The x and y values are switched. So if given the point 2, 5, xy 2, 5, in the original, we know that the inverse has the point 5, 2. The domain and range are interchanged as well, meaning that the domain of the original is equal to the range of the inverse. Kind of makes sense if our x's and y's are switching, our domain values, which are our collection of x's, and our range values, which is our collection of y's, are also switching or interchanging. And then graphically, the inverse function and the original functions are reflections over the line y is equal to x. So, as an example, here is a function, passes the vertical line test, so it is in fact a function with the domain of x is greater than or equal to 1, and range y is greater than or equal to negative 3. Notice we take a look at all the points that are listed here, 1, negative 3, 2, negative 2, and 5, negative 1. If we look at the inverse of this function, and look at the points that are graphed here, negative 3, 1, negative 2, 2, negative 1, 5, we see that we just switch the x and y values in each coordinate point as we move from graph to graph. Additionally, we should see that the domain of my original function is in fact the range of my inverse. Same values, just with the domain it was x and the range is y. And the range of my function is the domain of my inverse. Again, same numbers, just one with x and one with y, respectively. So these are inverses of each other, and when I look at them together on the same graph, we see that they are, in fact, reflections of each other across the diagonal line y is equal to x. They are the same distance across, mirror image. If you tilt your head a little bit, you could see they are, in fact, mirror images going across the line. All right, all inverse functions should have these properties. So let's go ahead and practice a few of these. Example 1, I want to graph these two functions, f of x and its inverse, to verify they are, in fact, inverses and state their domain and range. So graphing f of x, this is a cubic function, hk at 2, negative 3. Normal pattern for a cubic is 1, 1 in each direction, positive and negative, and then 2, 8 if I can fit it. And then negative 2, negative 8, I can't. So there's the graph of my original function. Okay, inverse function, hk here, at negative 3, positive 2 for this cubic. Cube root, we're going to go 1, 1 still, since it's positive, but now we're going to go 8 and 2. And negative 8 and negative 2 if we could, giving us the domain, giving us the cubic function there. Now, looking at this visually, yes, they are in fact reflections of each other across the line y is equal to x. Now, if I'm writing the domain of my yellow function, it should be the range of my inverse. We see the domain of the original function goes from negative infinity to positive infinity, always left and always right. So that means the range of my inverse, which we can see here, is also going negative infinity to positive infinity. The range of my function should be the domain of my inverse. Here we look, the range goes from negative infinity to positive infinity. And this is also negative infinity to positive infinity. So we see this switching. Now, it's not as clear here since they're both, all four of them are negative infinity to positive infinity. But as we get to harder examples, we know that the domain of the function is the range of the inverse. The range of the function is the domain of the inverse. Okay, let's take a look at this next. We have two lines to graph, g of x, negative 1/3 x plus 2, and g inverse, which is negative 3x plus 6. So take a moment in graphing these. G of x here is a linear function, y equals mx plus b. We start at a positive 2 on the y-axis, slope of down 1 over 3, down 1 over 3. For my g inverse, we have this function, again, slope-intercept form, y equals mx plus b, intercept of positive 6 on the y-axis, down 3 over 1 for my slope, down 3 over 1, down 3 over 1, down 3 over 1. as I look at these two graphs, yes, they are reflections of each other across the diagonal line y is equal to x. Now, we know the domain and range of our parent function is just going to be negative infinity to positive infinity, negative infinity to positive infinity, and that allows us to go ahead and get the domain and range for our inverse relatively quickly. Okay, now, on these particular functions, we were able just to graph it over the stated domain. Some functions require what we call a restricted domain to make the functions invertible, or basically have an inverse, or essentially pass the horizontal line test. The most common functions that require this restricted domain are quadratics, which we'll see in Algebra 2, and trigonometric functions, which cover in predominantly pre-calculus. So here's an example of this scenario. We're looking at the graph here of y is equal to x plus 2 quantity squared. So that means my hk is at negative 2, 0, which we see listed there. If I were to go ahead and switch all the xy values, if this was my original f of x, this would be my inverse, f to the negative 1. What we can clearly see here is just by switching all the x and y values, this new function, this supposed inverse, fails the vertical line test. Our inverse fails the vertical line test, and looking back at our original function, it failed the horizontal line test. So this is not a function, and our inverse is not possible. However, if I come up and I restrict the domain of the same graph, so here if I go from only graphing from negative 2 to positive infinity, so x is greater than or equal to negative 2 is the same as negative 2 to positive infinity. Now when I switch those xy values, I get this portion of the graph, which clearly passes the vertical line test, meaning the inverse is a function. So we can go ahead and fill in the domain of our blue function here. X is greater than or equal to negative 2. Notice it's just the restricted domain, which we now know is the range, y is greater than or equal to negative 2, of our inverse. And we know the range of our original function is from y is greater than or equal to 0, meaning the domain of our inverse is x is greater than or equal to 0. Okay, let's go ahead and try graphing these two quadratics over the restricted domain, then go ahead and graph their inverse and see whether or not we can get the domain and range of each function and inverse listed. I'll give you a few minutes to go ahead and moments to try that. Answer in 3, 2. Here are our answers. Now notice I graphed the quadratic in the full HK, but I only used half of it using only the restricted domain portion. So I left the other part dotted. So here, again, I graphed the full quadratic, but I made part of it dotted because I'm not including it, and I'm only including the portion with the restricted domain. X is greater than or equal to negative 3. So this one's going to be from the right of the vertex. So from there, I can just go ahead and switch the xy points and go ahead and plot them in there. Switch the xy points, plot them on there, and in my graph in red is the inverse. Filling in the domain and range, knowing that the domain of the function is the range of the inverse, and the range of the function is the domain of the inverse, we can quickly and easily get those values just by looking at the graph.